You know those moments in life when things just feel, well, kind of untamed? One minute
Mm-hmm.
you're checking the weather app, it promises clear skies, right? And the next, boom, you're caught in a downpour.
Happens all the time.
Or you're watching the stock market and it just seems to zig and zag with, I don't know, a mind of its own. It feels like pure chaos sometimes.
Mm-hmm. Unpredictable.
Exactly. But what if I told you that behind a lot of that apparent randomness, there's this fascinating, really rigorous world of mathematics, and it actually helps us understand and sometimes even use that unpredictability.
That's a great way to put it.
So today we're doing a deep dive into a concept that is just absolutely fundamental to making sense of these seemingly random things: stochastic.
Stochastic, yeah, it's a big one.
Our mission really is to unpack what stochastic truly means. Trace its origins back through math history, explore all the surprising places it pops up, science, daily life, you name it.
It's everywhere once you start looking.
And ultimately, discover why getting a handle on this idea can genuinely change how you see the world around you.
Absolutely. It's quite a journey we're embarking on. We're looking at centuries of really groundbreaking thought, moving from pretty abstract theory to incredibly, well, tangible applications. We've gathered a really rich mix of sources for you, some deep historical accounts, showing the intellectual struggles to really tame randomness, some nice intuitive intros to the complex math bits, and then a broad sweep of real-world examples.
Sounds great.
Prepare to see the hidden order in what often feels like just pure chance.
All right, let's dive in then. Let's unpack this. When we hear that word stochastic, especially, in technical fields, it can sound a bit intimidating.
It can, yeah.
But at its core, what does stochastic actually mean in plain language?
Okay, so at its most fundamental level, stochasticity relates directly to randomness. That's the key word. Think of it as describing processes where the outcome isn't perfectly predictable, right? Even if you know all the starting conditions. And this is the direct opposite of something deterministic. In a deterministic system, if you know the start and the rules, the outcome is completely fixed, foreseeable, every single time.
Right.
In mathematics, particularly when we talk about things like stochastic differential equations or SDEs, this randomness often gets baked in as a noise term in the equations.
A noise term.
Yeah, essentially it's like an unpredictable little kick or nudge that pushes the system in random directions.
Okay, I think an analogy might really help here.
Go for it.
Like, imagine a billiard ball on a pool table. Perfect conditions, no friction, whatever. You hit it with a certain force, certain angle.
Yeah.
You know exactly where it's going.
Yep, deterministic.
That's deterministic. Now picture a feather, and it's caught in this swirling, unpredictable wind.
Right.
You might know the wind's generally blowing, east, but you cannot possibly plot its exact winding path from second to second. That feather's movement is stochastic.
That's a perfect analogy.
And that random, unpredictable gust of wind, the noise term you mentioned, isn't it? Constantly messing with its path.
Exactly. That's it precisely. And, the journey to actually formalize this concept, to bring randomness into rigorous mathematics, it's such a rich story. For centuries, randomness was often seen as, well, chaotic, something outside the reach of precise calculation.
Yeah, like it couldn't be tamed by math.
Right. But the early groundwork for understanding these systems really owes a massive amount to people like A.N. Kolmogorov.
Kolmogorov, okay.
He was absolutely fundamental. He established a rigorous mathematical basis for probability theory, moving beyond just simple counting, like in dice games, to a more general way of measuring likelihood, even for continuous things like time or temperature.
So not just discrete outcomes.
Exactly. And it was his work, including this really pivotal paper in 1931, that helped formalize how continuous random processes, like the jittery movement of particles, Brownian motion, could be described. He showed they depend on just two key things: one parameter for their average direction or drift, another for the size of their purely random jiggle, the diffusion part.
Just two things.
And this allowed him to connect the probability distributions of these random processes to solutions of certain partial differential equations we now call Kolmogorov's equations.
That's just fascinating, taking something that seems so elusive, pure randomness, and then nailing it down so precisely you can link it to PDEs. It really shows the power of mathematical abstraction, doesn't it?
It absolutely does.
So what was the next sort of big conceptual leap after Kolmogorov laid that foundation?
Well, after Kolmogorov provided this, really solid measure-theoretic groundwork, Kiyoshi Ito made a profound conceptual jump.
Ito. Okay, I've heard of Ito calculus.
Exactly. Before Ito, mathematicians often looked at these random processes through what you might call an analytic lens, focusing more on the average behavior, the smoother parts. But Ito's integral, which he developed in the 1940s, it did something different. It really embraced the inherent randomness itself, the joggedness. It gave us the mathematical tools to deal directly with the completely non-smooth, unpredictable paths of processes like Brownian motion. This is a totally different probabilistic way of thinking, and it truly changed how we intuitively grasp these systems. It showed that dealing with the randomness head-on wasn't just mathematically sound, it was often more insightful.
So a real shift in perspective, not smoothing it out, but working with the roughness.
Precisely. And this new perspective, it really opened the floodgates. You had mathematicians like P.A. Meyer and Philippe Courage in the 1960s building on Ito's work, pushing the boundaries of stochastic integration, asking deeper questions about how these processes jump or evolve over time. Then came a really pivotal moment around 1970. C. Dolian's Date and P.A. Meyer, they made a breakthrough that truly generalized the whole theory.
How so?
Well, until then, stochastic integration was often tied to specific assumptions about the random processes, certain technical conditions. But they managed to remove some of those key restrictive hypotheses. It was like creating a kind of universal solvent for randomness, a truly general framework. This allowed stochastic calculus to be applied to almost any type of real-world random process you could imagine, even ones with jumps.
Wow.
And this critical step led to the coining of the modern term semi-martingale, which basically at that time meant the most general kind of process for which you could define a sensible stochastic integral.
Semi-martingale.
Yeah. And this generalization was absolutely crucial for the explosive growth of the theory in the 70s and beyond, especially in fields like finance, because suddenly they had the right mathematical language to describe all sorts of complex, unpredictable market movements.
It's incredible, isn't it? Seeing how science works, it's not just one single aha moment. It's this continuous, iterative thing.
Yeah.
Collaborative. Each breakthrough building on the last. Adding layers of insight, changing how we see things.
Absolutely. It's a fantastic example of that process.
Okay.
So with that history in mind, let's try and nail down what a stochastic process is at its heart.
Okay.
Think of it like a generalization of a simple random variable.
Yeah.
Like the outcome of a single dice roll.
Right. One random number.
Exactly. The stochastic process isn't just one random outcome. It's a whole collection of random variables that evolve and change over time.
Ah, okay. Like a random movie instead of a single snapshot.
That's a good way to think about it. And we generally distinguish between discrete time and continuous time processes. Discrete time is usually easier. It involves a sequence of events at distinct moments, like, say, the daily closing price of a stock. Finite or countable steps.
Makes sense.
Continuous time processes, though, they unfold over a continuous interval. Think temperature changing constantly. They need more advanced math, because time itself isn't broken into steps. It's a smooth flow, potentially changing at any tiny instant.
All right, that sounds trickier mathematically. Discrete steps seem simpler to model than that constant, smooth flow of change.
They generally are.
Can you give us some fundamental examples just to make this more concrete? What are some of the basic building blocks of stochastic processes?
Of course. Yeah, let's ground it. One of the simplest and oldest, actually, is the Bernoulli process.
Bernoulli.
Imagine just repeatedly flipping a coin. Could be fair, could be biased. Each flip is independent of the others, and each outcome is like a 0 or a 1, tails or heads. That sequence of flips is a Bernoulli process. Jacob Bernoulli himself was looking at games of chance using this idea way back in the early 1700s.
Simple coin flips, right?
Then you have something called the Poisson counter process. This models the number of events happening over time.
Events
Like phone calls arriving at a call center, or maybe radioactive particles decaying, or customers walking into a shop. NT is the count of events up to time t. The probability of an event happening in any small time interval follows a Poisson distribution. And the key things are, it starts at 0, 0, 0, and it has independent increments.
Yeah.
Meaning what happens in one time chunk, say between 1p meter and 2p meter, doesn't affect what happens between 2p meters and 3p meter. The arrivals are independent over non-overlapping times.
Okay. Random arrivals. Got it.
Exactly.
Yeah.
And perhaps the most famous example, the one we mentioned earlier, is Brownian motion, also called the Wiener process.
Right. The pollen particles.
That's where it started historically, yeah. Robert Brown saw pollen grains jiggling randomly in water under a microscope. But it was Norbert Wiener who gave it the rigorous mathematical description later. It's a continuous time process, modeling that kind of erratic, random movement. A key property is that its position at any time, pay, let's call it WT, follows a normal distribution, a bell curve.
Ah, the normal distribution.
Yeah, with a mean of 0, meaning it doesn't drift systematically on average, but its variance, its spread, is equal to t. So WT is distributed like N0T.
So the longer you let it run, the further it could potentially wander away.
Exactly. The uncertainty grows over time.
It's pretty remarkable how these seemingly simple models, coin flips, random arrivals, jiggling particles, how they become the foundation for describing such incredibly complex phenomena in the real world. They really are the fundamental building blocks, aren't they?
They absolutely are. And to really work with these stochastic processes, to analyze them and use them, we need some crucial conceptual tools.
Okay, what kind of tools?
Well, one of the most important concepts is the Markov process, or the Markov property.
Markov? Heard that one too.
The defining idea here is that it's memoryless.
Memoryless.
Yes. The future state of the process depends only on its current state, not on the entire history of how it got there.
Right, like your analogy earlier, the person navigating only knows their current intersection, not the whole route they took.
Exactly that. Where you are now is all that matters for where you might go next.
Okay. What else?
Another really vital concept is martingales.
Martingales. Sounds like something from sailing.
Huh. Maybe the name. But in math, it formalizes the idea of a fair game or a fair bet. The core idea is, if you know the value of a martingale process at a certain time, your best prediction for its value at any future time, on average, is simply its current value. It doesn't tend to drift up or down systematically based on past information.
So no edge.
Pretty much. Brownian motion, interestingly, is a classic example of a martingale. They're incredibly useful. They help show mathematically that you can't create a guaranteed winning strategy in certain random situations, like fair casino games. And they're essential tools for proving deep results in probability theory, especially about whether random processes eventually settle down or converge.
Okay, fair games. That makes sense.
Then we get to Ito's calculus and stochastic differential equations, SDEs. We touched on this.
Right, because normal calculus doesn't work on those jagged paths.
Exactly. Processes like Brownian motion have paths that are continuous, but nowhere differentiable in the standard sense. They're just too rough. So Ito's calculus is the specific branch of math developed to handle derivatives and integrals involving these kinds of processes, especially handling those noise terms properly in differential equations.
It's calculus for randomness.
In a nutshell, yes. There are specific rules, Ito's rules, for doing calculations, which are a bit different from standard calculus. And a defining feature, philosophically almost, is that it evaluates functions using the left-hand rule. Meaning it only uses information available up to the current moment, the present, or the past to determine the next infinitesimal step. It doesn't peek into the future, which is crucial for realistically modeling systems where you don't have perfect foresight.
This seems essential for modeling the real world.
It absolutely is. And one last core idea, conditional expectation.
Okay.
This is basically your best guess for the value of some random quantity given some information you already have.
Like my best guess for tomorrow's temperature given today's forecast.
Perfect example. It's not a guaranteed prediction, but it's the best statistical estimate based on the available data, the condition. It has a key mathematical property, sometimes called the partial averaging property, which intuitively means that if you keep making these best guesses based on information, they will average out correctly in the long run.
Okay, best guess based on what you know. That seems fundamental. Right, this is where it gets really interesting for me. We've talked about the history, the definitions, these mathematical tools, which are fascinating in themselves. But they become these incredibly powerful lenses for understanding the real world.
Exactly.
So what does this all mean for us practically? Where do we actually see stochasticity in action beyond the blackboard?
Oh, the reach is truly ubiquitous. It's not an exaggeration. Stochastic models underpin work in fields as diverse as, let's see, image processing, signal processing, definitely computer science, information theory, telecommunications,
Okay.
but also chemistry, ecology, neuroscience, physics, obviously, cryptography, finance, hugely, medicine, linguistics, even music theory, media analysis, color theory, botany, manufacturing, geology. The list just goes on.
Wow. Okay, so pretty much everywhere.
It helps us model everything from, say, the spread of an epidemic to the flow of traffic on highway to how neurons fire in the brain.
Okay, let's get concrete. Give us some compelling examples. Where does it really make a difference?
All right. In the natural sciences and physics, we talk about Brownian motion. But another huge one is the Monte Carlo method.
Monte Carlo, like the casino.
Exactly like the casino. It's a stochastic simulation technique. Physicists like Stanislaw Ulam and Enrico Fermi really popularized it during the Manhattan Project, actually. It uses randomness generated usually by pseudorandom number generators in computers and lots of repetition to solve incredibly complex problems that are just too hard for standard deterministic math, like simulating neutron diffusion in a nuclear reactor or modeling protein folding or complex fluid dynamics.
So using randomness to solve deterministic-seeming problems.
Sometimes, yes, or problems with inherent randomness built in. It's incredibly versatile.
Okay. What about biology?
Oh, fascinating stuff there. Ever heard of stochastic resonance?
No, what's that?
It's this really counterintuitive idea where adding a certain amount of random noise to a system can actually improve its ability to detect a weak signal.
Adding noise helps? That sounds wrong.
I know, right? But think about it. Sometimes a little bit of random jiggling can help a system jump over a threshold it otherwise couldn't, making it sensitive to signals it would normally miss. It's been shown to have potential benefits, for instance, in helping diabetic patients or stroke survivors with balance control. Applying tiny random vibrations to their feet can sometimes enhance their sense of touch and stability.
Wow. So noise isn't always the enemy.
Not always. Sometimes it's a feature, not a bug. We also see pure chance driving evolution through genetic drift. In small populations, gene frequencies can change randomly over generations, even with no natural selection pressure. An allele can become common or disappear just by the look of the draw.
Pure chance evolution. Okay, computer science.
Huge impact there. Randomized algorithms are a big field. They use random inputs or random steps to solve problems, often much faster or more simply than the best-known deterministic methods. Think about Google's PageRank algorithm. The original version used a model of a random web surfer clicking links, essentially a Markov chain, to figure out which pages were most important. Randomness is also key in cryptography for generating keys and in many areas of AI and machine learning.
Right.
And in computer graphics, things like stochastic ray tracing use Monte Carlo methods. They randomly sample light paths to create incredibly realistic images, simulating complex lighting effects like soft shadows and indirect illumination much more effectively.
So better movie effects thanks to randomness.
Pretty much.
Okay, finance. You mentioned that was a big one.
Oh, absolutely crucial. Stochastic models are the bedrock of modern quantitative finance. They're used to represent the seemingly random, fluctuating behavior of financial assets, stock prices, currency exchange rates, interest rates, you name it.
They seem random, but there are models.
Exactly. Models incorporating randomness. Financial analysts, quants, use these stochastic models constantly to value complex financial instruments, especially derivatives like options. The famous Black-Scholes-Merton equation, which won a Nobel Prize, is fundamentally a stochastic differential equation based on Brownian motion. It provided a theoretical way to price options, essentially by understanding and pricing the risk associated with the underlying asset's random movement using martingale theory.
So it let them put a price on uncertainty.
That's a great way to put it. It revolutionized risk management and trading. And really, this kind of thinking is at the heart of the whole insurance industry, too, assessing probabilities of random events and pricing policies accordingly.
Makes sense. What about media? You mentioned that briefly.
Yeah, it's used there, too. Stochastic modeling helps understand audience tastes, trying to predict maybe the opening weekend success of a film or TV show, analyzing patterns in consumer behavior for repeat business, things like that. And on a different note, there's a term you might hear in social commentary, stochastic terrorism.
Right, I have heard that.
It's used to describe rhetoric that doesn't directly order violence, but sort of demonizes a group or describes desired violent outcomes in a way that increases the probability that some listener acting randomly or independently, will be incited to commit violence. The idea is the rhetoric acts as a kind of random incitement. We're just noting the term's use here, of course.
Understood. Acknowledging the concept's application in that discourse.
Exactly. And one more quick one, manufacturing. Printing, even.
Printing.
Yeah, stochastic screening or frequency-modulated FM screening. It's a technique in high-quality color printing. Instead of arranging dots in a fixed grid, which can sometimes create visible patterns, it scatters tiny dots randomly. This can produce images that look sharper and have smoother tones.
Huh. Random dots make a better picture.
Sometimes they do.
It's truly astonishing, isn't it, when you step back? From the tiniest particles jiggling to the global stock market to how our own bodies work, even how we make images. This concept rooted in randomness is so precisely applied and understood across just a huge range of fields.
It really is.
It makes you realize that randomness isn't just messy chaos. It's actually a fundamental part of how so many systems operate, how the world works. So, as we wrap up this deep dive, I think it's really clear that stochastic isn't just about chaos or wild unpredictability. It's really about understanding, modeling, and sometimes even using structured unpredictability.
That's right. And it encourages us to recognize that randomness isn't always, a barrier to understanding. Often it's a fundamental component we need to account for. Thinking stochastically can give you a new lens to approach complex situations. You don't always have to fight the randomness. Sometimes you need to understand its structure, maybe even embrace it.
That leads to a great final thought for our listeners. So, what if the unpredictable nature of something isn't actually a bug, but maybe it's a feature? How might understanding the stochastic nature of things in your work, in society, even in your own decisions, how might that change how you approach problems? From navigating your commute, maybe, to making big life choices, or even just understanding global events.
It's a powerful shift in perspective. We really invite you to keep exploring this fascinating world where randomness meets structure, where chance has its own kind of order.